Whether you're trying to restore a spool that's absorbed moisture, or keep material dry throughout a long print, properly drying your filament can make a significant difference in both print quality and reliability. Over the years, we've covered plenty of filament dryers on this channel, and I've turned down a handful of them because I just didn't feel like they contributed anything meaningful that existing options didn't already offer. With the popularity of Bamboo Lab printers and the AMS, we've even seen options that add active drying to the standard AMS. However, the more affordable AMS Lite has all 4 spools completely exposed and out in the open, and up until now, there hasn't been a purpose-built drying solution for it. That's why I was interested when Sunlu offered to send over their new AMS Lite heater for testing. It fits around the entire AMS Lite, enclosing all 4 spools, and gives it active drying, while still allowing you to use it, as you normally would, for filament management and spool swapping. I've spent the past couple of weeks testing it, and in this video we'll cover the installation, features, performance, and I'll share my overall thoughts based on my time with it so far. So with all that being said, and without further ado, let's get right into today's video. Before getting through the unboxing and the installation, let's quickly run through its specs. When it comes to temperature, the dryer can be set anywhere from 35 to 70 Celsius. Sunlu lists support for a wide range of materials, including PLA, PETG, TPU, ABS and ASA, nylon, and even polycarbonate. For airflow, the dryer uses a dual-channel design that's supposed to help circulate airflow throughout the enclosure. This includes a heating element on both the left and right door, as well as an additional fan at the front and at the back of the unit. One pretty unique thing about this dryer that I haven't seen on any other units we've looked at is the automatic vents. There are 2 vents at the top of the unit that, when it is drying, open to allow for the release of humid air, and then as soon as the drying time hits 0, they close to sort of help seal the enclosure. There's a built-in sensor that tells you what the relative humidity is inside the dryer, and you can even enable a mode that automatically activates the dryer when the humidity rises above that target temperature. The safety features include door open detection, which lets out a slow continuous beep if you have a door open while the dryer is running. There is active or real-time temperature monitoring, so you can see what the temperature is at in relation to what its target temperature is, and it also has a built-in fan air detection. And of course, the biggest feature and the reason why you would be considering one of these is that it encloses the entire AMS Lite unit, turning it into sort of an active drying setup while still allowing you to use the AMS Lite. Today's video is brought to you by MicroSwiss. Based in the US, MicroSwiss manufactures high-quality 3D printer upgrades, including extruders, hot ends, and nozzles for over 150 printers. I've been running their hardware in my machines for over 7 years now, and I've always been blown away by their meticulous attention to detail. Their newest addition to the Flowtech lineup is the Hyper CHT nozzle. Its unique 6-chamber thermal geometry dramatically increases the surface area used to melt filament, allowing for up to a 95% increase in flow rate while also improving the inner layer adhesion. The hardened tip allows it to print with any material from your standards to your highly abrasives, and it's available in a wide range of sizes from 0.4 all the way up to 1 millimeter. Links are in the description to find out more about the MicroSwiss Hyper CHT nozzle, as well as all of their other available upgrades. The dryer came packaged nicely, and outside of needing your own AMS Lite, includes everything you'll need for the install. After removing the many strips of shipping tape that secured the unit, I found the necessary hardware packed within a thin piece of foam inside the enclosure. This includes a few self-tapping screws, as well as a long Allen key, the power cable for the dryer, and a small plastic cover. As for installation, this was a fairly simple process. Start by removing the stock stand from the AMS Lite, or in my case, the printed bracket that I was using to secure it to the horizontal top bar of my A1 printer. Next, open both side panels and separate the top and bottom halves of the dryer. The instructions just tell you to pull the 2 halves apart, but I tried that and it required a lot more force than I felt comfortable with. There are some clips, and I found that just grabbing a flathead screwdriver and pressing one of those clips out to release it made the entire thing come apart much easier, and that is definitely my recommendation to prevent accidentally cracking or damaging something on the dryer. Place the AMS Lite inside with its attached cable pointing towards the back of the dryer. You'll feed that cable through a small opening at the back and then use the included rubber grommet to secure it in place and also seal that opening so that way you don't have a bunch of air leaking in and out. The AMS Lite is then secured using the 4 included self-tapping screws through the original stand holes. Since these are self-tapping and we're going through plastic, be careful not to over-tighten them and accidentally crack something. We're just looking for snug. To install the top cover, start by removing the feeding assembly from the AMS Lite by taking out the 4 screws holding it in place. You also need to remove 4 screws from the top cover of the dryer so that the feeding assembly can pass through it. The piece you just removed from that top cover then gets installed beneath the feeding assembly where it acts as a riser. Reattach the feeding assembly to the AMS Lite, press the cover into the bottom half of the dryer, and reinstall the remaining screws. You'll also need to connect 2 small cables inside the unit that are used to control those automatic vents. These had a little bit more slack than I would have liked, and knowing myself, I wanted to prevent any future accidents, so I ended up printing out these little zip tie attachment anchors and VHB'd them in place, which just helped pull those wires a little bit closer to the inside body of the dryer. Once the unit was assembled, I connected the power cable and tapped on the power button to power on the dryer. Interfacing with the dryer is done using the screen at the front and the 4 capacitive buttons. I found that those buttons didn't always register my input, which may have been just a me thing, but my preference would have been to have had physical buttons. The overall interface itself is really simple to use. Tap the set button to cycle through the adjustable settings, then use the up and down arrows to change their values. From here, you can choose between 6 filament drying presets or relative humidity mode, switch between Celsius and Fahrenheit, adjust the target temperature or humidity level, and set the drying time from anywhere between 1 to 99 hours. 99 hours is a very, very long time, but one thing I would have loved to have seen, which doesn't seem to be an option, is to just have it set to stay on. At this point, I have a system in place for testing out filament dryers, so I started off by grabbing my thermocouple thermometers. This has 4 temperature probes, so I placed one just off the side of each of the doors, one at the very front of the unit, and another one at the back. I then selected PLA, which had a default target temperature of 50 Celsius, and began to monitor the temperatures. This is where things got interesting. After 5 minutes, the front measured 57 degrees. Both sides were around 53, and the back had already reached 70, 20 degrees above the set target temperature. By the 10-minute mark, the front had reached 70 degrees, the sides were around 65, and the back had climbed all the way to 82 degrees Celsius. With that initial temperature spike, I was really surprised to see just how much it dropped by the 15-minute mark. The front measured 54 degrees, the sides were around 53, and the back had fallen all the way down to 56. I continued monitoring the temperatures over the next hour. The readings gradually dropped further, while eventually stabilizing at around 50 degrees in the front, 47 to 48 degrees along the sides, and 53 degrees at the back. With those results, I was really curious to see what the readings would be like if I set it to its max temperature of 70 Celsius. So I started by letting the dryer sit overnight to come back down to just ambient temperature or room temperature, and I started to monitor temperatures again. After 5 minutes, the front measured 56 degrees, both sides were around 51, and the back was at 67. At 10 minutes, the front had climbed to 67 degrees, the sides were around 63, and the back had reached 80. And by the 15-minute mark, the front was up to 76 degrees, the sides were between 71 and 72, and the back had climbed all the way to 88 degrees. Just like with the PLA test at 50 Celsius, I continued to monitor these temps over the next hour to see where they fell down to and sort of what the settling point was. By the end of the test, the front had dropped to 58 degrees, the sides to around 55, and the back to 61, roughly 10 to 15 degrees below the 70-degree target temperature. Overall, both tests followed a similar pattern, which was an initial spike where all readings basically crossed over the target temperature, especially in the back. That was the biggest deviation, before finally settling or stabilizing. For PLA, the end result was pretty close to the requested 50 degrees Celsius, but for, I think it was set to polycarbonate, which was 70 Celsius target temperature, the ending temperature was anywhere between 10 to 15 degrees lower than what I'd set it to at the front of the unit. These probes are measuring the air temperature at specific points inside the dryer and not necessarily the exact temperature that the filament or spool that you're drying would be at, but still with that, 82 Celsius for PLA as the peak of what I saw is a lot higher than what I was expecting. And considering both of them followed the same pattern with a drastic spike in the back, it does show me that heat distribution certainly is not even. Before doing anything else, I wanted to see whether the initial spike in temperature could cause a spool of PLA to soften. After allowing the dryer to return back to room temperature, I placed a spool of PLA on the back left holder, which is the closest one to where I got that high temperature reading, and started the dryer. I also pulled out the thermal camera to just do a walk around and see if we could sort of get a better visual of what the thermocouple probes were reading. Sort of as expected, the warmest areas were around the heating elements located at the center, as well as along the bottom and back of the enclosure, where the internal heater fans would be pushing that heated air. From the outside, the highest surface temperature I measured was around 56 degrees Celsius, while the heating elements themselves appeared to reach approximately 75 degrees. After 10 minutes of drying, which is the point on both of my tests where that back corner had spiked the highest, I stopped the dryer and pulled out that spool of PLA to examine the material. The loose outer strand looked like maybe it had softened ever so slightly, but there wasn't any signs of obvious melting or bonding together. Pressing on and inspecting the wound filament, I didn't see any cause for concern. Next, it was time for the sponge test. For this, I take a sponge, cut it in half, and weigh it dry. I then saturate it with water and get the weight that it's at, place it in the dryer, and see how long it takes for it to return to its starting dry weight. I try to keep the starting conditions as consistent as possible across these tests. The dry sponge weighed 5 grams, so I added water until the total weight reached 20 grams. I then took the sponge and placed it on top of one of the spool holders, roughly centered where a spool would normally sit, set the dryer to 50 Celsius, and started the test. 50 Celsius is my standard temperature for this test because I'm more interested in overall drying efficiency than I am just brute forcing the sponge with as much heat as the dryer can possibly produce. I then checked on the sponge every 30 minutes, and it took a lot longer than I was expecting to return back to that starting weight. On average, it lost about 1 to 2 grams every 30 minutes and finally returned to its starting weight right around the 5-hour mark. For comparison, that is roughly twice as long as the last 2 dryers that I've tested. In every dryer video that I've done, I always get a handful of requests to try drying out a spool of filament and showing that. That is often easier said than done considering I live in a place that is relatively low humidity, but I wanted to give it my best shot. I had a spool of PETG that I knew I purchased a couple of years ago that's just been sitting out in the open on my rack, which felt like the perfect candidate. I found a Veroni or Veroni, I don't know how to pronounce that, bust of Spiderman, which had a ton of retractions, and just fired off a print without drying the spool to give us our starting point or our baseline. This may be the only time ever that I've been this excited to see the level of stringing that was on that first print. Next, I set the dryer to its PETG setting of 55 Celsius, and I let it run for 6 hours before printing the same model again. Compared to the original, there was a clear improvement. There was still some stringing, but significantly less of it. The print definitely still had some issues though, including one section that sort of just collapsed on itself. Based on the temperature results from earlier in 55 Celsius already kind of being on the lower end of drying PETG, at least in my opinion, I raised the target temperature to 65 Celsius, which I figured probably would get me closer to actually that 55 Celsius, and I let the filament dry for an additional 6 hours before printing it out one final time. Once again, there was a definite improvement. There was even less stringing than on the second one, but still stringing, and the section that had collapsed completed without any issues on this print. At this point, between the 2 6-hour drying sessions and it drying the filament during the 2 6-hour prints, I felt like that was plenty of time to get an idea of the real-world performance of the dryer. So what are my thoughts on the SUNLU AMS Lite Dryer based on my time with it so far? Well, let's start with the positives. Overall, I really like the concept. The AMS Lite is something that I've used quite a bit over the years, and while I've never really had any issues with it and it's been a solid system, one of its biggest drawbacks by far is that it just has your spools completely out in the open. And if you're living somewhere with higher humidity or regularly print with moisture sensitive materials, that is anything but ideal. Being able to enclose all 4 spools, actively dry them while still using your printer and the AMS Lite system is a pretty elegant solution. That being said, based on my testing, I have some serious concerns about the dryer's actual performance. The temperature behavior was pretty strange, with the dryer initially overshooting the selected temperature by a sizable amount before eventually settling below it, especially at the higher temperature settings. The back of the enclosure was also consistently warmer than the other areas, so heat distribution definitely isn't as even as I would have liked to see. The sponge test sort of reinforced this for me. While yes, the dryer did remove the moisture or the water from the sponge, it took right around 5 hours, which is twice as long as the last couple of dryers we've tested on this channel. And I think the PETG tells a similar story. The dryer clearly works, each print improved as the filament spent more time drying, but it took quite a bit of drying time to get there, and I even ended up having to increase the set temperature to compensate for the lower temperature I had measured during my testing. Based on the temperatures I measured, I can't recommend this dryer for high temp materials, as I simply don't think it gets warm enough internally to dry them effectively within a reasonable amount of time. For lower temp materials like PLA, TPU, and even PETG, I do think that it's capable of drying them, but if your spools have absorbed a significant amount of moisture, you might be waiting quite a bit of time to get them back to their initial state. Where I see this unit really being the most valuable is maintaining filament that's already dry, whether that's a brand new spool, or in my case, what I'm likely going to do is if I have a filament that needs to be dried, I'll throw it into one of my single or dual spool dryers that I know can dry it quicker, and then I can throw it inside of this unit, turn it on, and know that it will maintain that or help it stay dry. I still think the overall concept is really neat, and as far as I know, it is the only purpose-built dryer specific to the AMS Lite, so I think it's still going to have plenty of interest. I just wish Sunlu had spent more time optimizing the airflow and heater placement, because I think with better heat distribution and overall efficiency, this could have been a much more capable dryer. And that has been the Sunlu AMS Lite Dryer. I hope that you enjoyed this video and that you have a much better idea of what this is, what the installation process is like, and sort of what you can expect of it to see if it makes sense for your specific needs. If you have any additional questions, let me know in the comments and I will do my best to answer. As always, if I don't know the answer to your questions, I have no problem reaching out directly to Sunlu to try to get those answers for you. On that note, don't forget to like and subscribe for more great videos. We make a video just about every other week, so there's always fresh content coming your way. If you want to support the channel further, I'll have links in the description over to our Patreon, where there are some really awesome rewards. Huge thank you to all of our existing Patreon supporters. I appreciate each and every one of you for allowing me to come back every single week and spend more time doing what I love, which is making content for you all to enjoy. On that note, this has been Daniel from ModBot. I look forward to seeing you guys in my next video. Peace, guys!